Hello, my name is Moses Hajai. I'll be presenting to you soft problems on the exam practice questions on for food process technology. The first question I'll be presenting on is on a coaster, as you can see on your screen. A coaster has dimension. We've been given the dimension of the coaster to be 10 by 10 by 3 meter. Then the floor, the walls and roof have a similar construction of aluminium plate. Then we'll be given it a thickness of the aluminium on the inside, then 100 millimeter of insulation, and then 100 millimeter outside brick thickness. The inside storage temperature is given to us as -25 degrees Celsius, while the ambient temperature is given to us as 10 degrees Celsius. Now, the very first thing you need to find out is to determine the rate at which it would penetrate the coaster. Now, this includes the all walls, floor, and roof. Now, by calculating the temperature at the two surfaces and at the interfaces of the various materials, draw a rough sketch of the temperature profile through the walls of the coaster. Now, additional information that we are given include a thermal conductivity of the materials, which are aluminium, insulation, and the brick, and also the inside surface heat transfer coefficient and outside surface heat transfer coefficient. Now, these are very, very important. You need to take note of this. Now, why do you have inside surface heat transfer coefficient and outside surface heat transfer coefficient? Now, it's just telling us that the boundary layer, the boundary layer for inner boundary and the outer boundary is very, very important in this computation. Now to solve this problem, you need to understand what you are given, and then you need to understand, of course, what you are required to determine, what you are required to compute, and then the formula to establish the relationship between the given and what is required. Now, what are we giving? We are giving the coaster. We are giving a coaster of height of 3 meter. Then the length, the breadth are both 10 meter. Now, and then the thermal conductivity of aluminum. And for ease of computation, have used Ka for that, and that is 204 watt per meter per Kelvin. And then the thermal conductivity of insulation, I use Kn. The thermal conductivity of the brick, I use Kb. The inside surface heat transfer coefficient, I use Hi. The reason why I use Kn here is because I know I'll be using I as a subscript here, so it doesn't really matter. You can call this one HSI, but I just want to make it simple. Hi, then I use the second letter of insulation for this. It doesn't really matter. The most important thing is wherever you're supposed to use the thermal conductivity of insulation, you use the value of 0.04. That's the most important thing. And then the outside heat transfer coefficient is given to us as 5. Now I want you to note that this dimension you have here is for the this is for the dimension of the coaster. The figure you have here is for the entire coaster, and the dimension given are representing the length, breadth, and the height of the coaster. Now, if you look at each of the wall, we've been told that they are made of similar materials of aluminum, insulation, and brick, and we've been given the. Now, I'm going to draw that now. For brick, we have the brick. We've been given the thickness to be 100 millimeter. And don't forget, you need to convert that to SI unit, which is meter. Remember that 1000 millimeter equals 1 meter. So our the thickness of the brick in SI unit will be 0.1 meter, and I call that one SB. Now, remember I mentioned earlier that the boundary layer are very important. That is why I have something here to represent the outer boundary layer, and I have something here also to represent the inner boundary layer. Then the outside temperature is 10. The coastal temperature is -25. Now we have the brick here. We have the insulation, which is also 100 millimeters. So I use SN for the insulation. So don't forget that the thickness of insulation, and converting that to SI unit, you have 0.1. Then also we have we have aluminium, and then the thickness is 6 millimeter. and you also need to convert that one to SI unit, which is 0.006 meter. Now this is what we've been given. Now what are we required to find? We are required to determine the rate at which it will penetrate the coastal, which is defined as Q. The rate at which it will penetrate the coastal, this is showing in this line, which is Q, and we've been told that should include all the walls, the floor, and the roof. So our Q will be Q for walls, Q for floor, and Q for roof. So that is what we are required to find. Then that is part A. Part B, we are asked to draw the diagram, the temperature profile for this wall. And for us to do that, we need to establish the temperature at each of the interfaces. Now here we need to calculate the temperature at the wall, at the just outside the brick wall, and also the temperature just outside the aluminum inside the coastal. And again, it's also important for us to determine the temperature between the interfaces, for example between the brick and the insulation, which is T2, and then the temperature between the insulation and the aluminum, which is T3. Now going back to question number 1, we are asked to find the Q, the rate at which it will penetrate the coastal, Q. Now we are given the property of the materials that we use to construct the coastal. We know the property with brick, insulation. Here we've been given the property. You can see the thermal conductivity of each of the materials, and even the surface heat transfer coefficient. So that shows that invariably we've been given the parameters to calculate the thermal resistance. And again, here we have the cross-sectional. We can compute the cross-sectional area from this figure. We can find the area of the wall. Now we have one here, one at the other hand, one here, and one at the other hand. Now here the area of this wall will be this bit here, the 3 meter times 10 meter, which is 30 meters square. So we can compute the area, we can find the thermal resistance, and we have to find Q. Now that shows that what actually relate those parameters together will be the Fourier law, which is given to us as Q equals the area multiplied by change in temperature. Of course, we know the change in temperature, which is from 10 to minus 25. We can calculate that, and then we can also find out what will be our thermal resistance. Now here we have summation of thermal resistance. Now the question is, how do we calculate our thermal resistance? Now each of these layer we provide one form of thermal resistance or the other to the heat penetration. Now the outer boundary layer will provide a thermal resistance. The brick will provide a thermal resistance. Now the insulation will provide a thermal resistance. Aluminum will provide a thermal resistance. And then I know the thermal resistance by the aluminum is going to be very, very negligible because the thickness is very small, and again aluminum has the higher thermal conductivity, so the resistance is going to be very low. Now then inside the coastal we have the inner boundary layer. We also offer another form of thermal resistance. Now the question is, how do we calculate a thermal resistance from the parameter we're given? Now here we are given the inside, this is outside. We are given outside surface heat transfer coefficient of H naught. So the thermal resistance for R naught will be 1 over R naught, 1 over H naught. Sorry. Now that is going to be 1 over H naught. Now that's the thermal resistance for the outer boundary layer. Now then the H naught is given to us as 5. So we have 1 over 5, which is going to be 0.2. Now remember, the formula here is down, so if you are bringing them up, is here we have it as a denominator. It's going to be going up as a numerator. Now if we have here minus 2, m raised to power minus 2, when it goes up it turns to m raised to 2. Now here we have k raised to power minus 1. When it goes up it turns to k. This is like saying k raised to power 1. So it's k. 1k is equal to k. So now for W, we have it as a denominator here. When it goes up as a numerator, it's going to be raised to power minus 1. Take note of that. So we have the thermal resistance being generated by the outer boundary layer to be 0.2. Now let's look at the thermal resistance from the inner boundary layer. it's going to be 1 over h1. So it's going to be, you're going to be using the, instead of using the outer, you'll be using the inside surface heat transfer coefficient instead of outside. So because this is for thermal resistance from the outside, from the outer boundary layer, this is thermal resistance from the inside boundary layer, so inner boundary layer. So we have that one to be 3. This has been given to us as 3, so it's going to be 1 over 3, and it's going to be 0.333, same unit as we have there. Now for the brick, you know that the outer boundary and inner boundary layers is a form of moving fluid. Moving fluid, that is why we have 1 over h. Now for the brick, this is a solid. The thermal resistance for the brick is going to be the thickness of the brick divided by the thermal conductivity of the brick. Now the thickness of the brick has been given to us as SB. So the thermal conductivity is, I call that one KB. So here we have a brick is 0.75 for thermal conductivity, so it's going to be 1 over 0.75. Sorry, 0.1, which is the thickness. This is not 1, please. It's 0.1, the thickness of the brick, not 1. So 0.1, that you can see meter, yeah. So it's a thickness, it's not 1. 0.1 meter divided by 0.75, which is the thermal conductivity of the brick. Now look at the unit now. Now if you divide 0.1 by 0.75, you have this. Now for the unit, now meter is up there. Now this is meter raised to minus 1. When this one goes up, it turns to meter square, because this meter cannot cancel this meter. They cannot, because this meter is raised to minus 1. When it goes up, applying the laws of indices, it's going to turn to meter square. Now k is raised to minus 1 here. When it goes up, it turns to k. Now this is w raised to power 1. When it goes up, it turns to w raised to power minus 1. When you move it from numerator to denominator, you raise it to a power of negative, or for example, if it is negative, it turns to plus. If it is plus, it turns to negative. So that is, you can just take note of the unit, and you can see that RB and RI, despite using different formula, they have the same unit. You can see they have the same unit of meter square Kelvin per watt. That shows that we can add them together. Now you use the same thing to find your Rn. Your Rn would be the thickness of the insulation divided by the thermal conductivity of the insulation. So we have this. This is our Rn. You can see our insulation is offering a higher thermal resistance. You can see a higher one because it's an insulation is offering a higher thermal resistance. For the aluminum, you can see it's going to be offering a very low thermal resistance, because aluminum is a good it conducts heat very easily, unlike the insulator. So we have that one there. Then we have the inner boundary layer. We've already estimated that. We've already calculated that. So putting them together, you have this. You have 3.1666 meter square Kelvin per watt. So we've been able to establish the thermal resistance, the summation of thermal resistance. Then we need to find the change in temperature, which is 10 minus 25. So change in temperature is the temperature outside minus temperature in the cold store, and temperature outside is 10 minus 25. You have 35K. Now to find the area, we still need to find the area. Now area, we need to find the area for wall, which is 3 times 10. This is 1. Another one, 3 times 10. Another one, that they have the same dimension. So which means calculating one, we know the others. Now for the roof, it's different. We have 10 times 10 for the floor, and 10 here times multiplied by 10 for the roof. So we have for the roof or for the floor, they are the same. So it's 100 meters square, and then for the wall is 30 meters square. So to now find the, remember this formula, the Fourier formula, Q equals A dt divided by summation RT. Now we want to find the Q for the entire cold store. Now the Q for entire cold store will now be 4, because this is for the wall. We have 4 walls, multiplied by the Fourier law for the wall, which is area of the wall times temperature difference divided by thermal resistance, now plus the Fourier law for the floor and plus Fourier law for the roof. So we have that. Now you discover that delta t and summation RT as the same. They are the same, and they are, so we can take them out. By the time you take them out, delta t over summation RT, you have 4 area times area of wall plus area of floor plus area of roof. So we've taken delta t over summation RT out. We've taken this out, so we are left with AF AR. Here we've taken this and this out. We are left with AW. Then we have 4 for here. So we have, this is what we've taken out. This is going to be easy to compute. Now by the time you put in the figure, you have this. 35K is the change in temperature. Then summation RT, we've done that before. This is what we have. Then 4 times 30, we've done the area for wall before. Area for floor 100, area for roof 100, and is in meter. They are all the areas. They are in meter square. Then we have the unit is here. Then by the time you can see now, K we cancel K, meter square we cancel meter square. Then W is raised to power 1. This W will go up. By the time this W goes up, it becomes, is raised by -1. Sorry, it's raised by -1. By the time it goes up, you have W. So it's raised by -1. It goes up to become W. So by the time you add them together, you have 320 times 35 divided by that. You have your final answer to be 3,536.92 watts. And the implication of that is that the rate at which it will penetrate the core store, the entire core store, is approximately 3,535 watts. That is part A. Now to go to part B. Part B is asking us to find the temperature at the interfaces, temperature at the wall, at the inner boundary layer, at the wall, and also at the interfaces. We have called them T1, T2, T3, T4. You can call them anything. Now the most important thing is that you use the appropriate figure when you are doing your computation. Now the T1 is the temperature just outside the brick here. Because of this outer boundary layer, because of the outer boundary layer, temperature outside is going to be different from temperature you have at the brick wall. So that's why I call it T1. Then the temperature between the brick and the insulation, I call it T2. Temperature between the insulation and aluminum, I call it T3. And the temperature just inside the core store at the wall, at the aluminum wall, is T4. Because of the effect of the inner boundary layer, so -25 is going to be different from what you're going to be having here. It's because the inner boundary layer is going to be offering a form of resistance. So we've been able to find the resistance for each of the layers. And then one thing I want us to note is temperature difference is proportional to thermal resistance. Now what does that mean? Now the temperature difference between this point and this point is a function of this thermal resistance. Now the higher the thermal resistance, the higher the temperature difference. The higher the temperature, thermal resistance, the higher the temperature difference. Now what that's supposed to mean? It means that the temperature outside, let's just take this formula in now. The temperature outside, which is 10, minus temperature at any point, maybe here or here or here or anywhere, temperature at any point, divided by the overall change in temperature, which is 10 minus 25, now will be equals to the thermal resistance up to that point. Now don't forget, at any point will be equal to thermal resistance up to that point divided by overall thermal resistance. Now don't confuse yourself. Now let me explain what this means. Now for example, if you want to find the temperature at T1, temperature at T1 will be temperature outside, which is 10 minus T1 divided by overall change in temperature, which is 10 minus 25, equals the thermal resistance up to that point will be 0.2. It will be R0. From here, from 10 to this place is R0. That's the thermal resistance. And the overall thermal resistance is for everything. Which is 3.1666 meter square Kelvin per watt. Now To calculate, now let's just try and find out what we need. We need overall change in temperature, which is given to us as which is 10 minus 25, which is 35. Then we also know we know our overall thermal resistance, which is 3.116. Now, in order for us to calculate T1, to compute T1, this is 10 outside minus T1, overall change in temperature is 35. This will equals to thermal resistance up to that point. Thermal resistance up to that point is R0 divided by the overall thermal resistance. Now, this will definitely equals to, you know that R0 is 0.2. Now, this will equals to that if we can just, because we need T1, we take this one away to the other side. Now, is here as a division, as a denominator. It's going to go here. Once it crosses the equality sign, it goes there as a multiplication. So don't forget that it goes there as a multiplication. It has crossed the equality sign. It goes there as a multiplication. Now, so we still the same thing. We still have the same thing here, other than 35 has been moved from here down here as a multiplication. So to do that one in your calculator, you have this. Then this 10 is this side, is on this side, but we need T1. We need to free our T1. So we need to take this one to the other side. If you want to take it to the other side, once it crosses the equality sign, it turns to negative, turns to minus 10. So we have minus 10 there. So we have minus T1 equals 2.2106 minus 10. So we have negative, we have minus 7.7894. So we have minus is here. The minus, we cancel out minus sign. So we have our T1 to be 7.7894. The implication of that is temperature just outside the brick wall here is approximately 7.8. Now, that is T1. If you want to calculate T2, the question I want to ask is, what will be the thermal resistance up to that point? Can you tell me that? Oh, good. That will be 0.2 plus 0.133. You need to sum them together because we want to find T2. So the thermal resistance up to that point will be the summation of that. So let's just quickly go and solve that. So to compute T2, same protocol, same procedure, sorry. So R0 now, because we want to find T2, is 10, temperature outside is T10, it does not change. Then temperature at any point is T2, overall change in temperature is this 35. Then our thermal resistance up to that point, which point? T2 will now be R0 plus RB, which is 0.2 plus 0.133. Follow the same process, follow the same procedures. You get your T2 to be 6.3161. So the same thing for your T3. That will be this up to that point, because we are coming from this side. Up to that point will be this one plus this one. I mean R0 plus RB plus Rn. Now let's go and look at how that is done. Now don't forget that T2 is the temperature and the interface between the brick and insulation. Now to compute T3, we use the same procedure. R0, RB, Rn. That is the thermal resistance up to that point. So put in all the figures and find out. You can see 0.2, 0.1333 plus 2.5 up to that point. You can find out that our T3. Now let's just look at something here. Now the same thing here. Now 10 is going to be going to the other side. Now we have 31.316 minus 10, because it's plus 10 here, it's going to turn to negative at the other side. So our T3 now, our minus T3 is 21.3161. So if minus T3 is this, so our T3 will be minus 21.3161. That shows that the temperature at the interface between the insulation and the aluminium is minus 21.3. Now to do the last one, which is the T4, still the same procedure, sorry. So we have R0, RB, Rn, Ra, R0, RB, Rn, Ra, because we want to find the temperature up to this point. So substituting every necessary figure, you have you discover that because the thermal resistance being offered by aluminum is very negligible, you will discover that our answer will be very close to C3. You know, the other time we got 21.3 minus 21.3 for C3, just because the thermal resistance being offered by aluminum wall is very negligible, just because of the thickness, and again, aluminum is a good conductor of heat. So we have that to be T4. Now we've been able to find out our T1, T2, T3. So let's, having obtained your temperature for T1, T2, T3 and T4. Now we can now have our temperature profile drawn for the wall. Now we know that outside we have 10 degrees Celsius. Now for in between the outer boundary layer and the brick, we have 7.9 degrees Celsius. Now between the brick and insulation we have 6.3 degrees Celsius. Now between the insulation and aluminum we have minus 21 degrees, minus 21.3 degrees Celsius. And just outside the cold store, just inside the cold store, we have minus 21 degrees Celsius also for T4. Now then inside the cold store itself we have minus 25 degrees Celsius. So from this we cannot do our temperature profile, and this is what we have now. And I hope you really enjoy this the video. And for references, please use Agile, OM and TZL 2014, then Food Process Technology Practice Questions and Solution Video 1. And if this approach has been of help, and we would like to hear from you, please email your feedback to myself at majayhi@lincoln.ac.uk or Lindy at ltizi@lincoln.ac.uk. Thank you very much. Bye.